Welcome back to Samagra Shiksha online classes. Namaste. My name is A. Mahalakshmi, working as CRPPS in KGBP Tuni, East Godavari district. Hi children, how are you? I hope all of you safe at home. Today we discuss the topic about atoms and molecules. In previous chapters we can learn some of the terms like compounds, elements, matter, metals, non-metals, etc. But in this topic we can learn these topics as atoms and molecules, how they are prepared into matter, etc. And also some of the greatest scientists also and their inventions we can learn from this chapter. Keywords.
Atom, molecule, law of conservation of mass, Lavoisier, and chemical reaction.
So children, let us learn about atoms and molecules. All of you know about the word matter. Either it is a living thing or non-living thing. Matter is made up of molecules. Matter is made up of molecules. And how the molecules are made up of? With the help of the atoms. What are atoms? Group of atoms combine to form a molecule. Group of molecules combine to form a matter. Here atoms are indivisible. Atoms are indivisible. We are unable to divisible the atoms. In group of atoms combine to form a molecule and group of molecules combine to form a matter. Either it is a living thing or non-living thing. Example, let us observe the example. I am writing with a piece of chalk. All of you know. Okay. So, piece of chalk is made with calcium carbonate, CaCO3, calcium carbonate. Here, three different types of elements are combining to form a substance. Here, what are the three different substances? CaCO. What is Ca? Calcium. Ca is calcium. C, carbon. And O, oxygen. So the three types of particles combine to form a matter, calcium carbonate. In previous form, we can learn this type of particles called as Anu and Paramanu.
We see and feel around us is usually termed as matter. By now, we even know that matter is classified into three major states. And what are these three states of matter? That's right, they are solid, liquid, and gas. But have you ever thought about what the matter around us could be made up of? Well, this question is not new and has been addressed a long time ago. And many people have made an attempt to answer it. Let us have a look at a few of these philosophies and theories. Recorded evidences suggest that around 500 BC, an Indian philosopher named Maharishi Kanad hypothesized a concept. His curiosity about components of matter made him put forth an idea. He suggested that when we divide matter into tinier particles, ultimately we reach a stage when the matter cannot be divided further. These particles which cannot be divided further make up the matter. The matter was called Padarth in the Indian language and he named the particles as Parmanu. On similar lines, another Indian philosopher named Pakhuda Kathyayama made slight modification in Maharishi Kanad's work and elaborated saying that such indivisible particles come in different combinations to make up different kinds of matter. Around the same era, two Greek philosophers also suggested the same concept. The two personalities were Democritus and Leucippus. They also postulated that if we divide matter continuously, then we reach a stage where it cannot be divided further. These indivisible particles does make up the complete matter. Democritus named these particles as atomus, meaning indivisible. Now you may say that this concept is known to us. Yes, I agree, but we are familiar with this concept now. In the era when people were not really aware of anything in science, such concepts proved useful in laying the foundations for modern inventions.
Word as Anu and Parmanu. Okay, so in this matter, we can learn the atoms, molecules and matter. From this we can learn previous sessions, we can learn the related topics, elements and remaining. Okay, this is the minimum basics for the chemistry part. From this we can learn remaining topics belonging to these topics. All of you understand, children?
French aristocrat and chemist Antoine Laurent Lavoisier was an incredibly important figure in the history of chemistry, whose findings were equivalent in stature to the impact of Isaac Newton's discoveries on physics. His new structure of chemistry, which understood the constituent parts of air and the process of combustion more clearly, set chemistry on a modern road and laid the groundwork for Dmitri Mendeleev's work and the creation of the periodic table. Lavoisier's work overturned centuries of incorrect thinking about the nature of elements and compounds. Lavoisier's most notable book Traité élémentaire de chimie, published in 1789 by the elite French Academy of Sciences, could be considered the first modern chemistry textbook, and contained theories about the nature of elements which replaced the phlogiston theory. The belief that there was a fire element was contained within all combustible objects, which were released in the form of fire, heat, and light when an object burned. At the time, the development of chemistry was being held back by this widespread and erroneous belief. The theory and the name phlogiston was coined in 1718 by Georg Stahl, a Bavarian professor of medicine. The essence of it was that combustible substances contain a curious substance called phlogiston, which they lose when they burn. Because balances were inaccurate, the fact that substances often gained weight when they burnt was often missed. And so firm was the belief in phlogiston that when a gain in weight was recorded, it was explained away, for example, by saying that the phlogiston was an incorporeal ethereal fire that was lighter than any other known substance, and buoyed up heavier ones, or even a substance with negative weight. Before Lavoisier published his Traité, aided by his wife Marie-Anne Pierret, who learned English to help him translate the growing body of scientific research, helped him with experiments, and drew all the diagrams, the phlogiston theory was accepted as fact by the leading chemists of 18th century Europe, and the four-element theory of the elements was mostly accepted, or not denied, by most chemists. Building off the work of Anglo-Irish natural philosopher Robert Boyle, who in the 17th century defined an element as a substance that cannot be decomposed into any simpler substance. Lavoisier revived this definition, and proved its accuracy through extensive and rigorous experimentation. Lavoisier was concerned with improving the lives of the public, and the origin of his discoveries about elements began with a project in 1768 to improve the supply of good drinking water in French cities. At the time, there was no effective method for measuring the quality of water chemically, so he had to rely on measuring the density, a physical measure. Since the most widely accepted theories of the time said that, when water was heated some of it turned into earth, measuring its density would clearly be confusing, and the results questionable. To better understand the process, he created an experiment to learn more. By heating an amount of distilled water in a sealed container over 100 days, he found that the weight of the container had not changed. Even more interestingly, he found particles of earth floating in the water, and that the weight of this earth matched the decline in the weight of the container after it was emptied, meaning that it must have come from erosive actions of the water on the container, and not through the conversion of water into the earth. This was a huge discovery that ultimately would overturn the dominant thinking of 2 centuries of chemistry. Later, in experiments with phosphorus and sulfur, he found that the substances absorbed air on burning, and increased in weight. He wrote and left a sealed note to the Secretary of the Academy on 1 November 1772, proposing that this effect might occur in all substances. Further extensive experiments showed that elastic fluids, what we would now call gas, absorb different amounts when burned with different types of air. When powdered metals, or calcinates, were burned in an enclosed space, they absorbed different proportions of the weight of the air in the containers, ultimately suggesting that air, once considered an element, was in fact a mixture of a compound. During the winter of 1782-83, he collaborated with his friend and mathematician Pierre-Simon de Laplace, and published a paper in the Academy attacking phlogiston theory as imaginary, saying that it did not exist within metals or any other substance, and that the process of combustion and calcination of metals was easier to explain without it. Later, Lavoisier learned about experiments by English scientist Henry Cavendish, who had obtained water from the burning of inflammable air, hydrogen. Lavoisier replicated this and explained that water must not be an element, but instead was comprised of a compound of hydrogen and dephlogisticated air, oxygen. His greatest and lasting achievement was to impose order on the language and symbolism that have shaped the thoughts of chemists. The trait was intended as a beginner's guide to chemistry, and included a table that recognized 55 elements with the old and new names. Metals were now shown to be compounds of metals with oxygen, hence vitriol of Venus became copper sulfate. When the French Revolution began in 1789, Lavoisier was working on the process of respiration and transpiration. His earlier work suggested that these processes were a form of combustion, and that the heat an animal gives out is due to the conversion of inhaled oxygen into fixed air or carbon dioxide. After the Academy was suppressed in 1793 by the Revolutionary Committee, he was arrested, convicted, and executed without trial on 8 May 1794. As Douglas Mackay wrote in the introduction to the 1960s edition of The Trait, thus perished the most illustrious victim of the revolution.
Lab activity. Let us see the lab activity. What is our aim? To find out the change in the mass before and after a chemical reaction. So what are the metals required here? Sodium sulfate, spring balance, barium chloride, small test tubes, distilled water, retard stand, conical flask, rubber cord, etc. So these items are also present in our mixture tubes. Let us observe the items. Sodium sulfate salt, barium chloride salt, retard stand, wash bottle with distilled water, 2 beakers, conical flask, small test tubes with the test tube stand, spring balance, spatula, rubber cord, etc. So let us start our activity. What we say first? Take the barium chloride salt, open the cap. With the help of this spatula, take how much amount? 2 grams of barium chloride in the beaker. Okay. This is barium chloride. Then add distilled water. Pour the water. Then mix with iron rod. So barium chloride solution is ready. Similarly, I will keep this side. Then with the help of this spatula, close the cap of the barium chloride and keep it aside. Then take sodium sulfate salt. Open the cap. By using this spatula, take 2 grams of sodium sulfate into the beaker. Okay. Close the cap. Keep it aside. Then again, by using wash bottle, pour the water into this test tube. Mix the sodium sulfate solution. Okay. So here, sodium sulfate solution is ready. Sodium sulfate solution is ready. the sodium sulfate in water? Then freeze. Keep it aside. Okay. Next, take 4 ml of barium chloride salt in the little test tube by using the filler. Why we are using this filler? We can easily transfer the substance from one item to another one. Okay. Then pour it in the small test tube. Then thread the test tube mouth with the help of the thread. Why we are threading? When we are placing in the conical flask, it does not touch the solution present in the conical flask. Okay, so that's why we are threading the small test tube. Keep it aside in the test tube stand. Then hang the test tube. After hanging, then take sodium sulfate solution carefully without mixing into this one. So we are taking the sodium sulfate solution. Okay. Then this is one item and this is another item. This is barium chloride and this is sodium sulfate. Then place the barium sulfate solution into it without touching the solution. Observe this carefully, children. Okay. Then keep the rubber pot. What is this? Rubber pot. And press the lid like this. Are you understand? Then weight by using the spring barrels, we can weight this one. Okay. Carefully we can do the activity, otherwise observe this activity, children. Are you understanding? Okay. I am hanging the test tube, the spring balance. So this is spring balance. So I am hanging this test tube. Observe the reading. Are you understanding? Barium chloride is in the small test tube. Sodium sulfate is in the large conical flask. They are not mixing. We are weighing both the masses with the help of the spring balance. Understand? Then note the weight of this. Reading in the notebook. After that, what can I do? I am mixing both the barium chloride and sodium sulfate solution. Okay, I am using, that is we are tying with the thread at the mouth. Okay, so I am completely mixed both of the solutions in the conical flask. Are you observing the changes in the test tube? Change So I am mixing both of the solutions in the test tube. Again I am keeping the rubber pot. Again I am weighting with the help of the spring balance. Okay. Again I am weighting with the help of the spring balance. So what do we observe? Is there any weight change or color change? What we observe? With the help of the retard stand, we can hang the test tube like this. Why we are hanging with the help of the retard test tube? Why? Because
From this activity, what is the result? A chemical reaction takes place and the mass remains same before and after the chemical reaction. Therefore, mass is neither created nor destroyed in the chemical reaction. Law of conservation of mass. The total mass of the product formed in a chemical reaction is exactly equal to the mass of the reactants. This is known as law of conservation of mass.
Worksheet.
Worksheet. Answer the following questions. Define law of conservation of mass. Who is called father of modern chemistry? And the third question, did you observe any precipitate in the lab activity?
Thank you.